Okay, well, we're going to go ahead and get started. If you can just make sure that you can hear us online. If somebody can just either raise a hand or something, or just speak up, that would be helpful. I just want to make sure people can hear.
Yes, we can hear.
Thanks. Wonderful. Okay, well, welcome everyone. This is a great day. So we're here to hear Vimig Socrates' PhD dissertation defense. And it's great to see a lot of friends and families and other PhD students that are here today. For Vimig, I will start and I'll just give a brief introduction of who I am for those who may not know. So I'm Andrew Taylor. I'm in the Biomedical Informatics and Data Science department, and then also an emergency physician. And Vimig has been working in my lab for the last couple of years. I think what you're going to see today is really, really interesting. There are tons and tons of questions around the topic that he's going to discuss. I'm on this kind of list board for people who are kind of focused on diagnostic reasoning and medicine, and there's all kinds of discussion around Bayesian reasoning and uncertainty quantification and how that's going to play out with a lot of these large language models moving forward, because it becomes this central aspect of some of these diagnostic systems. But I also want to highlight, because I think you're going to get a general impression of kind of all of the stuff that Vimig has worked on for his PhD. But he's done a ton of other things in our lab, a ton of other projects. He has helped. We've built a chatbot to interface with another chatbot to do some bias assessments. He's worked with countless other teams to be able to provide additional assistance on that. I think he's learned how to interact with physicians too a lot, and learned a ton of like the medical lingo. So I've been impressed now that he can pronounce like a lot of the antibiotics and things. So I learned an immense amount. He's been a fantastic student. And I can't wait to hear this. And I think without further ado, I'll let you go ahead. Thank you very much.
Thank you so much.
You made it again.
Yeah, I'll close things up. Step out of the way. Hey everyone. Okay, just gonna hide stuff. Cool. Alrighty. Okay. I will get started. So, Andrew, thanks for the introduction. I appreciate it. Yeah, thanks everyone for coming in person as well as joining on Zoom. Yeah, so I'll talk through some of the work that I've done, as well as some of the like past projects that I've worked on, and sort of how they have inspired some of the work that I did in my dissertation over the last year or so. So the title of my dissertation is Uncertainty Quantification and Bayesian Reasoning in Clinical Applications of Large Language Models. And so a little bit of, is this gonna work? Okay, cool. Just a little bit of background on what I'm gonna go through. Yeah, I'll talk through some of my prior projects and then do a little bit of background that's relevant to sort of how I'm framing the dissertation as a whole. And then I'll go through like the three main projects that I had as part of my dissertation and how those are sort of helping us draw some conclusions around the framing that I've put into it. Just as a little bit of history. So I started my PhD in 2019, and around 2017, 2016 is when the current iteration of language models came around. And so those are BERT models and GPT, the first iteration of GPT models. And so these are some of the projects that I worked on that Andrew just mentioned in the past. And these are largely concerning conventional language models. And we did a bunch of sort of information extraction type tasks where we were trying to pull information out. So I won't go into these in great detail, but if you are interested in any of those, feel free to chat with me outside. And then obviously with the current introduction of large language models, we started to do some work in there. We did worked with one of the other med students in our lab and a bunch of other collaborators to evaluate whether or not LLMs can do sort of reasoning in the classical like answer questions on the medical licensing exam task. And then lastly, we do some comparison between the two in some of our more recent projects. So that's kind of where we started. And a lot of what we learned when we were doing that was that it seemed to be the case that these LLMs don't tend to reason at all in the way that humans do or physicians do. And so that got us thinking, how do they reason and how do those things differ or how are they similar? And so this is sort of the overall framework that I'll be taking for the projects that I've worked on. So we have some sort of LLM, and most of my work is done on closed LLMs, which are LLMs where we don't have the underlying model to access in any way. And so I mostly worked with GPT models with OpenAI. And so I designed sort of 3 different experiments that I'm hoping will kind of give us a sense of the cognitive processes of physicians and allow us to compare that to the way that LLMs might reason. And our goal here is to sort of identify potential biases that these LLMs may have with respect to these cognitive processes. And so I'll obviously go through each of these projects in some detail, but one of the things that I wanted to highlight here is obviously LLMs are not humans. They don't think like humans, and it's important to not anthropomorphize them and say that they think or reason or anything like that. But I am taking this sort of cognitive lens. These experiments were originally designed on humans, but I'm taking this lens because I think it helps us sort of frame some of the ways the classical error modes that LLMs have, and it might help us highlight the kind of problems that LLMs are good at and the kind of ones that they're not good at. And so I think hopefully you will see that as I talk through these things. I just wanted to highlight that that is the case. And so, also, sorry, I forgot to mention this at the top, but feel free to stop me at any time if you have any questions, either here or on Zoom. I will try and keep an eye on the chat. Okay, so to get started, I just wanted to do a little bit of background on LLMs. You all, I'm sure, have used ChatGPT at length, and there's tons of resources. Jay Alamar does some really good blogs on how they work, and so I'd encourage you to check those out. It's where all these GIFs come from, but I'll just do a very brief overview. So if you have these 6 words, recite the first law of robotics, this is a little bit misrepresented. So a model will initially read in all of the text at once. So when you put in, you type into the prompt, it'll read everything in at the same time. But then when it's generating text, so, it'll generate the first word A, robot, I think is the next word. And so as it's generating that it'll be will be done in sequence. And so it'll use the context of the previous word to infer what the next word should be. And so that's sort of why you see that like typewriter text when you're using ChatGPT. Of course, like when we're looking at this initial prompt, not all these words are equally important to whatever you're trying to generate. And so there's a way of sort of weighting how important those words are. And that mechanism usually is called attention. And so there's a bunch of different types, but I'll just give a very brief overview. And so if we look at this, the second law of Isaac Asimov's laws of robotics, a robot must obey the orders given it by humans, except where such orders conflict with the first law. So in that sentence, the word, the pronoun it refers back to this word robot. And so it's important for the LLM to recognize what the context and the meaning of that pronoun is within this context of the sentence. And so when we look at an LLM, you can think of each of these words as having some list of numbers that represents the word and the meaning of the word. And so when we're trying to generate the new word after the word it, it'll particularly attend or focus in on the words A and robot because those are relevant to the generation of that next set of sequences, that next set of text. So that's a little bit of how this process works. And I just wanted to talk very briefly about the training process. And so when you have a GPT model, of course, all of the ones that I've worked with being closed models are already trained on a significant amount of data, but when these models were trained, they're trained on huge volumes of text, both from the internet as well as books, both open books and controversially copyrighted books. So when you're training a model, you have some sort of input sequence here. A robot must, and the model during training might generate the word exterminate. But in reality, the true end of that sentence is obey. And so when you're training that model, it will try and nudge the model towards trying to generate words like obey when you see that initial sequence of a robot must. So just getting back to our central figure here, I talked a little bit about LLMs, but I wanted to talk a little bit about clinical cognition in general and how we can use some of the findings in the last like 40, 50 years or so to give us some insight into the way that LLMs might reason. So there's sort of two main paradigms in clinical cognition that I'll be talking about here. There are others, but these are the ones that I think will help us think about the experiments that I'm going to talk about. So the first one being the hypothetical deductive framework, and that's sort of the classical like scientific method. You can think of a patient coming into the ED. Most of my work is in the ED, and so a lot of my examples are going to be coming from there. So a patient shows up in the ED, and they do their initial examination and present their problem, and a physician might be coming up with some initial set of hypotheses, either 3, 4, or 5 hypotheses, and they'll kind of be trying to figure out what kind of data they need to gather to either confirm or reject those hypotheses. And you kind of go through that iterative process until they're reasonably confident of the final diagnosis, which they can then treat or triage or whatever else they need to do. However, that's like a fairly intensive reasoning process. And so, a particularly adept physician might just see a patient and recognize that they've seen similar patients like that before. And it's sort of a more holistic evaluation. And so largely this is like described in cognitive science literature as some sort of pattern recognition, or you can think of it as like there's some sort of prototype of patients that you've seen before, and you're trying to see if that patient will resemble the current one that you're looking at. One of the ways that this has been broken down into in further detail are with these things called illness scripts. And so there's essentially a couple different pieces of information that need to go into an illness script. So the first one being some initial conditions, and so those are things like prerequisites for the patient. So they're male, they're a smoker, those sorts of things, and then sort of information from the initial initial presentation as well. So like, they're sweating or they have shortness of breath, whatever. And then those sort of, along with some amount of intuition from the physician, will lead to a final diagnosis. And that's sort of like how the pattern recognition component works. But one of the big issues was in the cognitive science literature and also in clinical cognition, how do we decide which system is used, and how do we know whether physicians flip between them? Are there other sort of qualifying factors to that? Things like expertise. And so if you've read Thinking Fast and Slow by Kahneman, and his other work is with another guy named Tversky. And so they did a lot of this work trying to figure out how we can bring these two models together. And so you can think of them as having two different systems. And so initially, patient presents to the ED. There is some amount of like cognitive work going into figuring out whether or not that patient has been seen before or similar patients. If they have been, then you go through the lower cognitive load, the easier task of just doing pattern recognition. If that's not the case, then they're going to do that more complicated task of hypothetical deductive reasoning. There's higher cognitive load, it takes more time. But one of the advantages, and this is again, there are obviously some caveats to this, but when you're looking at that system one sort of pattern recognition reasoning, there are a number of biases that occur. And those are the kind of biases that we're hoping to also mimic or represent when we look at the LLM. But in the clinical case, what that might look like is, let's say the patient shows up and they're like, oh, my stomach hurts. And like, I went on WebMD and I think I have diverticulitis, right? So like, there is the potential for the physician to say, okay, let me either really focus in and hone in on that particular diagnosis rather than doing sort of a broader evaluation. And so that's a bias called framing effects or premature closure if they decide to diagnose that patient early before they have all of the evidence. Another example is when they first make a diagnosis and maybe they're really getting a lot of confirmation bias associated with that diagnosis, and they don't take a step back and do further evaluation to see if there's anything else that could possibly be the case in the differential, which is sort of their working set of hypotheses that they have. So I'm hoping to kind of talk about some of those sorts of diagnoses or biases, sorry. But before I do that, I kind of wanted to bring those two things together. So the clinical cognition and the LLMs. And so there was some work done a few years by Mar and Poggio, and they sort of came up with 3 different ways that we can evaluate any computational system. And there's like a ton of different ways to like slice and dice this, but the way that I'm looking at it is the first level is computational, which is like, what is the purpose of a system and what do they do, and how do they, what problem are they trying to solve? The second one being sort of algorithmic, which is like how do they do it? What is the like in my perspective, looking at like what is the sort of process by which they're solving this? What is the, in this case, the reasoning process? And finally, the implementational. So that's sort of at the hardware level or maybe a slightly higher level. What are the implementations that need to go into that? And so I'm looking at the algorithmic level, sort of using a cognitive psychology lens. And one of the examples that you could break that up into is, the higher level problem might be summarizing a scientific article. But there's a ton of different ways that, we would summarize scientific articles. So does the LLM do that a sentence at a time, a word at a time? Does it look at everything holistically? Would be sort of the level that I'm working in. But obviously you can go further down. And if you remember that attention mechanism that I talked about, there are different ways that you could attend over a piece of text. And so that might be closer to the implementational level. And there is some work on sort of splitting these up further. And so you could obviously do that. And it kind of is just a lens by which we would look at, what level we're evaluating the LLM at. Okay, so that's some amount of background on this. And feel free to let me know if you have any questions about any of that, but I will dive into the actual work that I've done over the past year or so. So the first project that we were looking at was on deprescribing, which is sort of a framework of removing medications in older adults. So medications in general in older adults has led to, especially if you have a lot of them, has led to a lot of negative health outcomes like adverse drug events, admissions to the ED and falls, things like that. And so there's sort of like a structured process and a framework by which some physicians have tried to remove the medications that patients might be prescribed. And so I won't go into great detail on this, but essentially what you would need to do is figure out exactly what meds they're on. A lot of older adults don't know. And so they're just like, here's a box of pills. So you need to figure out what they're actually taking. And then you would identify the relevant ones and then start that process of deprescribing them. And of course, you have to monitor them, make sure there's no side effects associated with removing a medication, any drug-drug interactions you're not noticing. So I wanted to talk a little bit about where that uncertainty comes in. So I'll talk about this when we actually do our project, but some of it comes from identifying what are called potentially inappropriate medications or PIMs. So these PIMs have a list of criteria that different organizations have released on how to actually deprescribe them. But those criteria are somewhat ambiguous, and so it's something that I'll talk about, but there is some amount of uncertainty that comes from that. Another aspect of the uncertainty is associated with the clinical context itself. And so there are, the patient might not have represented the information correctly. There might be something that you're missing when you're diagnosing them, those sorts of things. So there is some uncertainty to the clinical context, especially when we're looking at information from the EHR. So the way that the information is represented in the EHR is not actually, exactly mirroring the patient's state. So I just talked a little bit about the three different types of criteria. And so these are the three that we mainly looked at. I'm not going to go into great detail here, but these are some examples down here. You can see obviously beers is like very straightforward. There's just a certain type of medication you'll want to avoid. The other ones have a little bit more context. And they're from, both the UK and the US and a couple of different organizations. GEMS-RX is one that's more recent, specifically for the ED, which is why we included that one, but the other two are very relevant and are very commonly used. And so there have been some approaches to try and make these computational. The criteria lists are pretty complicated, and it's a lot of work for a pharmacist and a physician to go through and actually make these deprescribing recommendations. So when we do that, there was a study that came out that tried to do this and just sort of make structured rules to input that into the EHR. And what they found was a lot of the criteria, so both in STOP and beers, there's a ton of information that's needed aside from the medication itself. And those are things like the indications, the schedule, other values like labs and vitals, things like that. And so one of the things that we thought would be interesting is to see if an LLM can parse all of that EHR data and determine whether or not these medications need to be deprescribed or not. So that's what we did. And so this is sort of the pipeline that we use. So we took patients in that age group that I mentioned, so 65 years or older, and they have 5 active medications. We took some of their structured information and unstructured information, and we sort of broke it down into 2 steps here. Initially, when we ran this, we just gave all the criteria to the LLM and tried to make it do recommendations. And there was a lot of conflicts. It was unable to determine which criteria were relevant, or even to the medication, much less whether or not the recommendation should have been made. And so we split it up into a step of filtering the criteria initially, where we have a huge list of criteria, and just based on the medication, the LLM will determine whether or not the criteria are something that could potentially apply. And then the second step is to actually make the deprescribing recommendation based on that clinical context. The last bit is sort of a structured evaluation that we did where we compared it to medical students. And then we also looked at who was correct when comparing to medical students, keeping in mind that they are trainees. So like we had an senior physician compare and figure out if the LM was right or the medical student was right. There's some other ways of evaluating this that I'll talk about closer to the end. But that's sort of the high level pipeline. Unfortunately, what we saw was that when we did this initial criteria filtering, there were a ton of criteria, and not all of them were particularly relevant. And so here's an example of that. So, statins for primary cardiovascular prevention generally should be deprescribed, but in cases where there is established frailty or an expected life expectancy of less than 3 years. And that is, both of those, qualifiers are very ambiguous. They definitely don't exist in the EHR in a structured way, and they might not even exist in the EHR in general. And so those sorts of criteria we considered high yield. And so we tried to remove those and filter for the ones that are more relevant. So for an example of that is macrobid for individuals with creatinine clearance of less than some threshold. And so in that case, we have just a single lab value that we have to find in the EHR. So that makes it much simpler. So those we considered more high yield. So the process by which we did that was we had a consensus study where we gathered 7 experts and asked them to evaluate all of the criteria across a couple different dimensions. The first one that we were looking at was computability within the EHR. So we asked them 4 different questions. For example, how easy is it to find that information in the EHR? How much other information do you need aside from that? And that sort of gives us a sense of whether or not the EHR contains the information necessary to calculate these criteria. The other element of this is the clinical risk. So we want to make sure that we're deprescribing things that would have a significant impact on the patient if they weren't deprescribed. And so using those two, we can plot, all of the criteria, and we pick basically this top right quadrant, and 50% of that quadrant is what we end up with, which is around 80 criteria or so. So when we look back at this initial set will be 80, and then that'll be filtered down to, whatever number is relevant to the medications for that patient. So the first part of this is evaluating against the medical student, which is what I'll talk about now. So this is a confusion matrix. A lot of you would have been familiar, but if not, this is what it looks like. And essentially what it is along the x-axis here are recommendations made by the GPT model, and along the y-axis here are medical student annotations. And so this column here would be cases where the LLM believed that there was no criteria relevant to that medication at all. The middle column is there are relevant criteria, but the LLM doesn't recommend deprescribing. And the last column is there are relevant criteria, but they do recommend deprescribing. And so when we look at this, one of the things that we notice is a lot of the medications in general, over half of them, slightly over half, don't have any relevant criteria at all. And so there's a fairly small number that we are actually looking at that reasoning process with. In that reasoning process, one of the things that we see is that the GPT model is far more likely to recommend deprescribing when compared to the medical students. So you can see that this 42 number versus the inverse of that, where medical students believe that recommendation of deprescribing was important when the GPT model disagreed. And so I think we have some hypotheses as to why that might be the case based on that cognitive lens that I'll talk about in a little bit. But the other big thing that we had to do was compare and figure out who was actually correct. And that also allows us to look at some of the different types of error modes that LLMs come up with. So this is across those 2 steps, how the LLM did. And so when compared to a medical student, upon adjudication or reviewing of those disagreements, we see there is a significant improvement for the GPT model in that filtering step. And so we think that that's a fairly straightforward task. Essentially, it's some amount of semantic information retrieval, where it's just trying to figure out whether or not the medication exists in the text, compared to the more reasoning process of looking and making that deprescribing recommendation. There is the GPT model wasn't as good as the annotators, although that difference is less significant. So, like I mentioned, we looked at the different ways that LLMs can error out, and we used sort of an existing taxonomy of different types of errors that reasoning models come up with. And so here are some examples of what that might be like. So one of the big ones was an incorrect reasoning step somewhere along the reasoning chain. And so an example of that is a GPT model recognized amlodipine as a calcium channel blocker, but not as an antihypertensive. And so in the criteria, it mentions antihypertensives. And so the GPT model missed that particular case. Similarly, GPT recommended deprescribing QT prolonging antidepressants when there was no history of any QT intervals at all or any ECG data to refer to, which are necessary for that deprescribing criteria. So there's not information there, and we think that there are cases where the LLM is sort of leaping to conclusions without supporting evidence because of the way that it was primed. So I'll talk about that in just a little bit, but the section that I hadn't talked about before, this is a couple of the different ways that we can prompt LLMs to give us information. And when we're looking at it sort of in collaboration with physicians, can we use the LLM to and the confidence that the LLM has in itself to determine whether or not there are some cases that are too difficult. And so essentially what we did was we asked the LLM to provide its own confidence. And then in practice, the way that this would work is if it's not confident enough, it would be passed off to manual review by a physician because it's too difficult for the LLM and the LLM thinks it's ambiguous. Unfortunately, that didn't work. So what we saw was along this x-axis here is the differing fraction, which is the number of times that, or the percentage that the LLM decided to push off its decision to a manual reviewer. And so ideally what we want to see is something along this diagonal where the harder the cases are, the LLM pushes it off more often, and we see an improvement in performance. Unfortunately, you can see along both of these axes that these numbers are pretty small. And so in general, the LLM doesn't seem to be well calibrated or have a good understanding of its own confidence. And we tried this with a couple different methods, and none of them seem to have any impact. So one of the things to note here is that this partly is due to the fact that the LLM's confidence distribution is heavily left skewed. And so you see, like, even in the lowest cases where it definitely should have been less confident, it has a minimum confidence around 60%. And so it's still fairly confident. And so that's something to, that's potentially one of the reasons why this might occur. So getting back to our initial diagram, looking at some of the potential cognitive biases, again, caveat being that we can't know exactly what these biases are because we don't have a good sense of those underlying mechanisms, but these are potential ways that mechanisms by which these errors might have occurred. So the first one being framing effects. And so like I mentioned, we prime the LLM to recognize that it's doing a deprescribing task, and that's something for it to focus on. And so doing that may have given it the potential overconfidence to focus in on cases where it might not have enough information, but it still makes that deprescribing recommendation. Similarly, a poor understanding of sort of real world probabilities is a potential reason for this. I did, just as an aside, chat with the LLM, and it doesn't seem to have a great understanding of sort of real world likelihoods of actually making deprescribing recommendations. Of course, if you work with LLMs, you know that they're brittle and there's not a lot of coherence between different questions that you ask it. So there is a potential that despite it not knowing how often deprescribing actually is done in the real world, maybe it can do it well, but that's one of the potential reasons where that might be the case. So that's sort of the first project that I worked on, and that's sort of more of a management task. A medication has already been prescribed, and we're trying to treat the patient further. But one of the other things that we wanted to look at was, in the diagnostic setting, what are the sort of biases that occur? And so the way that we did that, or I want to give a little bit of background on Bayesian reasoning before I get into that. And so we've got this guy here, Thomas Bayes. He's a fun guy to Google. He was a minister and he's written 2 big papers. One of them is on God and the other one is on Bayes theory. So I would encourage you to look him up. But the math part, which is the interesting part, or actually they're both pretty interesting, but the math part, which is more relevant to the talk here, is this thing called Bayes theorem and Bayes rule. In the clinical setting, the way that this works is we have some symptoms, a patient presents and we don't know what their underlying disease is. But we want to figure out what that disease is based on the symptoms that they have. And so that can be represented as the probability of symptoms given some unknown disease. And we also have the likelihood of diseases in general. And so using those 2 pieces of information, we can compute the likelihood of a disease given the symptoms that the patient might have. So this is just the math for that. And you can represent this as odds ratios, which is how I'll describe it now. So in the past, before we had computers and stuff, physicians would use tables like this. This is called a nomogram. And the way that you'd use this is you have your probability of a disease. Let's say, for example, a patient comes in and their chest hurts. You might try and figure out if they have acute coronary syndrome or not, which is ACS. And so you might say, okay, they have like a 25% chance of ACS. And you might run a lab test. The relevant lab test here is getting a value of troponin, which is sort of a protein that is released into the body when you have heart damage to the heart. And so when that's the case, you might say, okay, a positive troponin has a likelihood ratio of around 10. And so you draw a line and you say, okay, then I think based on that positive result, they have a likelihood of having acute coronary syndrome of 70%. If that was negative, instead, it would drop down to around 15%. And so that's how you'd use this. And this sort of framework is the same thing that we're evaluating with the LLM. So the way that we did that was looking at a bunch of vignettes that were initially developed for training medical students on this sort of reasoning. And we also wanted to check race. We wanted to check a few other sociodemographic factors, but we weren't able to because they influence sort of the prevalence of the disease. So we mainly looked at race, and those don't seem to have an impact on the diseases that we picked. But the first question would be, you have a guy come in with progressive shortness of breath. What is the probability that he has congestive heart failure? The next question we'd ask is provide the sensitivity and specificity, which are sort of diagnostic criteria associated with a particular lab value, in this case, chest x-rays. And we say use information based on this description as well as your judgment. And then we finally provide those results. So we say a chest x-ray was performed, it was negative. Now, what is your likelihood of that disease? And so what we see is this is a little bit difficult to read, but it's not super important to know what all these specific numbers are. We didn't see any main significant differences by race, but you obviously see significant differences by condition here. And so we have ACS, CHF, pulmonary embolisms, and pneumonia. And in general, what we see is that as we add more sort of accurate Bayesian information, the LLM seems to perform better. And of course, if we give it all the information, I'm sure you've tried this. If you give it a bunch of math problems, any GPT model, it'll perform fairly well. And that's what we see. But one of the things that we're thinking is that doing that numerical reasoning doesn't necessarily mean it's understanding the underlying clinical context. And so that's what we tried to show. So if we look at the estimated likelihood ratios, you can see they're very much different from the true likelihood ratios that the LLM has, although they are variably different. And so for example, in chest x-rays for congestive heart failure, that is very, very off, and that influences the probabilities. And so this is sort of the error rate compared to the true likelihood that the LLM should have estimated. This is compared to, for example, D-dimers, where in that case, they're much closer to 0. So in general, like I mentioned, we don't see any significant differences due to race, which is a good thing. But we do see that the LLM is able to reason explicitly when given all the Bayesian information, but we believe that that potentially masks some of the underlying biases based on the different diseases and the information that the LLM might have about that. One of the reasons might be because those are differently represented in the training data set. And so there's different amounts of information the LLM has. And then finally, that is largely driven by how much knowledge the LLM has about the diagnostic accuracy of a particular lab test. So again, looking at this figure, some of the potential heuristic biases that we have here are, again, we see that poor representation of real world probabilities, where the LLM isn't able to recognize how effective a particular lab test is. We also saw this as conservatism bias, where cases that are highly predictive, so congestive heart failure, ACS, and pneumonia, sorry, not ACS, but the other two, generally chest x-rays, are the LLM seems to sort of have more, I guess, lower or more mean-oriented likelihood ratio. So it's not further out at the extremes, but rather closer to the means. And of course, one of the confounding factors may be just that it doesn't have a lot of information about chest x-rays. And so that might be one of the driving factors as well. Okay, so we wanted to extend this work a little bit. And so we wanted to try and figure out, not just for a single reasoning test, so not just getting a single piece of evidence, can it determine what the diagnostic process is and make the, calibrate its probabilities, but over time. So presenting an initial patient over time, can the LLM sort of update its confidence? Can it figure out what the right diagnosis is? What pieces of information does it ask for? Those sorts of things. And so that's what we did in this last study. I'll start with, just a little bit of background on the cohort that we were working with. We were looking at all patients in the last 8 to 10 years or so that showed up with chest pain. And because we work in the ED, we were mostly looking at these diagnoses that are particularly life-threatening and also rare. And so these are definitely like rule-out diagnoses that you need to make sure the patient doesn't have before sending them home. So there's 7 different ones. And of course, you can see the prevalence here is very, very low. And so that definitely was sort of an inhibiting factor in training some of our models that we use to infer this diagnosis, evaluation. But being in the ED and keeping in mind that these are the ones that needed to be removed, we decided to go with that limitation. So we took structure information and notes, again, just like in the prescribing project, and we trained what's called a Bayesian network. And so this helps us get some additional information and base some of our reasoning. And so a Bayesian network essentially looks like this. This is a very classic example where we're trying to figure out whether or not a patient has TB or cancer. And for example, whether or not they have TB is influenced by whether or not they've been to Asia recently. And so you can sort of draw these connections between different pieces of information and how these probabilities influence one another. And so we trained a model for chest pain. I won't show it here because it's huge and confusing, but this is essentially what it looks like. So once we had that Bayesian network, we can go through our actual evaluation. So we took a single patient, and obviously we did this repeatedly to get all of our data, but we took a single patient and we gave all of the information that a patient would have, that a physician would have at triage. So that's like how old they are, how sick they are based on triage levels, and what their age is, chief complaint, those sorts of things. And we prompted the LLM to ask for information. So we said, okay, what information do you want to be able to diagnose this patient? In this case, maybe it asked for a lab value and it said, I want the troponin value. And so this is the first time that we can start to use our Bayesian network. And so if we have that actual value, we just provide the value. And this study was done in a similar way with a classic data set in bioinformatics or biomedical informatics called Mimic. But we're doing it obviously with our local data, and they did sort of bias their evaluation by not being able to provide information that they didn't have. And so instead, we can refer to the LLM, to the Bayesian network to figure out information that may not actually exist within the data set. And so the way that we do that is we have some information associated with the Bayesian network, and we can select that those things are true, and then we can figure out what the value would have been for patients like that one. And then we provide that value instead. And so we provide that information back to the LLM, and then we say, okay, what additional information do you need now? And we sort of go through this iterative process until the LLM is confident enough to make a diagnosis or assign the other diagnosis label. And so one of the things that we were interested in was how the different ways that we can prime an LLM influence whether or not it's able to make this diagnosis. So we came up with a couple different prompting strategies. The first one is to just give it the list of diagnoses that were relevant. And so we gave it the full list and we said, we are interested in these. If none of these applied, then assign a different diagnosis. But we were also curious, based on that sort of real world probability hypothesis, can we provide those really low prevalences to the LLM, and does that influence its decision making? And then finally, if we don't prime the LLM at all, looking at the sort of framing effects, does the LLM make the same sort of decisions it would otherwise? And essentially what we did was we categorized those diagnoses just based on whatever the free text that the LLM outputted. And so the evaluation that we did at the end was we obviously compared it to what the physician's diagnosis was. We also looked at the confidence over time to see if those confidences are representative of what a physician might do. And then finally, we compared to the quote unquote optimal, which is the last way we use the Bayesian network. We define the optimal diagnostic pathway as looking at the next diagnostic test that most reduces the uncertainty associated with any particular diagnosis. So, okay. Again, these are confusion matrices that I showed last time. These are actually the differences between adding prevalence and removing that prevalence. The first thing that we see is that in general, the LLM seems to not make as many incorrect recommendations associated with ACS. And so it's able to recalibrate to some degree based on having information about the prevalence back to saying, okay, there are more cases of other diagnoses than there are of ACS. Of course, we do have some issues where now it's assigning other diagnoses to cases that really were ACS. And we also see that trend sort of furthered if we compare it to removing any diagnosis information at all and just having it output free text. And so again, we see the same thing where it's able to recalibrate its probabilities, but maybe it's overcompensating to some degree. So again, we looked at how the confidence changes over time. And so essentially what this is a distribution of the confidences of the LLM across our patient population at each step in the conversation. And so ideally what we'd like to see is, very low confidence at the beginning, and then that increasing over time as a diagonal, as it gets more confident towards the end. Unfortunately, we don't see that. In general, what we see is that the LLM has essentially the same level of confidence, which is fairly low throughout, except right at the end where it seems to increase closer to 60%, although with much higher variance, meaning that there are cases that the LLM seems to have a lot of confidence, and then a lot of cases that it doesn't have a lot of confidence as well. And so this is one of the ways that we show that, those probabilities aren't aligned with its actual reasoning process. So like I mentioned at the top, we were also looking at what kind of information is requested. And so in general, what we wanted to see here was that we were curious if you used ChatGPT before, you know that like a lot of times when you're asking it to do something, it'll ask you for a ton of information before it does that thing. And so we were wondering if in a clinical case where all of those things cost time and money, if it still is doesn't care that additional pieces of information need to be collected. And so in general, we see that actually the physicians tend to request more information. This spike that you see in vitals is mostly due to the fact that in the ED, the vitals are all gathered at once, pretty much continuously. And so the LLM has to request these pieces of information one at a time. And so that's why you see a spike there. The only case that that's not true is in imaging, where physicians probably recognize that, imaging costs time, money, and resources. And so they don't request them that often, whereas the LLM doesn't really seem to care about that. The last thing that we compared was the overlap between that quote unquote optimal diagnostic pathway and the LLM. And so in general, we see very little overlap between those two things. And actually, this isn't missing. It's just that there was almost no overlap for esophageal ruptures. So one of the reasons that this could be is that when we trained our Bayesian network, I didn't show the results here, but because the prevalences are so low, our network wasn't amazing at classification. So maybe its recommendations aren't as quote unquote optimal as they otherwise could be. We did try and push it towards that rule out perspective. So we tried to increase how often those diagnoses were given and reduce the false negatives so that we reduce that a little bit, but that's still definitely a limitation here. So that's still something that we're trying to figure out how to handle and see what that overlap could be using a couple different metrics. So finally, just looking at the heuristic biases here, I've talked about these a few times, but again, we see those framing effects where if we don't provide any information about those diagnoses, the LM seems to improve in its prediction and more aligned to the prevalences that actually exist within the real world. And again, same with the real world probability. So we see that adding in those prevalences also seems to make some improvement. Okay, so that was a lot. Hopefully it was all good. Nobody fell asleep. So I'll just briefly recap what I've learned throughout this time. So in the deprescribing project, there were cases where the LLM seemed to leap to conclusions because we told it you're going to do a deprescribing task, even though it didn't have the sufficient evidence for that. And similarly, it may not recognize that those low levels of actual deprescribing in the real world have an impact. So there were cases where like it was trying to deprescribe like diapers and like insulin test strips and stuff, which like don't really matter. And so adult diapers, these are all adults. Okay, so and then biases. So we didn't have framing effects there, but we did see miscalibration of probabilities associated with the lab testing. And finally, we saw cases where if we remove the information associated with what diagnoses we're interested in, that seemed to improve performance as well as the prevalence. So I just had a couple ideas on how we can use this information to potentially improve LLM reasoning in the clinical space. The first one is, like I said, we're using black box models. And so we don't have access to the underlying model to retrain them. And so what we can take advantage of is something called function calling, where we can reach out to an external data source of some kind and use that as additional context when the LLM is reasoning. One of the ways that that might work is, so you would have seen function calling, if you use ChatGPT, it might like go ask Wolfram Alpha to solve a math problem for you and then provide that result. One of the ways that we can use it in probabilistic reasoning is, let's say we have a local cohort and we're trying to prime the LLM to reason within our local cohort. We can reach out when, let's say, for example, the physician is trying to figure out if a patient has sepsis. We want to know how often sepsis occurs in our local cohort. we can have the LLM make a function call out to our local database, get that query, return it back, and then use that as additional context. And so obviously there's a lot of things we'd have to figure out here, like how we want to include that question, how we want to include the context that's returned, et cetera. But I have some potential hypotheses that this might help. If we do have access to the underlying model, we can use the same process, but sort of fine tuning. And so we can generate a set of epidemiological data. So for example, things like how often does sepsis occur? How often do two comorbidities happen within the same patient population? And then provide those answers numerically, and then fine-tuning the LLM may potentially calibrate some of those probabilities back to what the real world should be, at least within our local cohorts. Okay, that's all I've got. So I was going to go through and talk about all the people that I have to thank for everything, but I will pause here and see if anyone has any questions. What's up? Oh, yeah. Thank you.
Yeah, and I guess we can start with committee members' questions and open it up to the larger group. You have open question session, and then we will allow the rest of you all to go, and then we'll have a closed question session for another 20 minutes or so. And then, yeah, then we'll break after. So.
Anyone have any questions? Yeah.
So in the third project is describe over the conversation for diagnosis. Right?
Yeah.
Does your evaluation actually evaluate the process of conversation? Because you just mentioned, oh, what's the final diagnosis? It's actually quite critical, right? Does the LLM ask the right question?
Yeah.
Which leads to the final.
Yeah, I think, yeah, so that is something that we would like to do, but that, requires a lot more physician annotation and figuring out, what are the types of errors, we have to classify those. And so I sort of took as much of a structured approach as I could by comparing to the optimal reasoning process that the Bayesian network released, came up with. But yeah, ideally, that's what we would want to do next, is to actually look through the text that's being generated to see if the reasoning within each of those conversation steps makes sense. Yeah.
To piggyback on that, so
Yeah.
Similarly, how does the structure of the information actually provided to it, not just the sequence, impact the ultimate reasoning that the LLMs or explain?
So you mean like what do you mean by the structure of the information?
So when we talk about
Yeah.
diagnostic pattern, we talk about the diagnostic conversation, and
Right.
that relies on the physician asking particular questions, but it's in
Mhm.
on to sequentially narrow down.
Yeah.
In this case, you're tossing a bunch of information at it
Right.
in a structured fashion in a couple different ways, so network to vignette. So
Mhm.
bit of an integration problem, and I know you've done other work in related contexts beyond the simple fusion tasks.
Yeah.
How does that the structure of that information being passed to the LLM in order to have it render a decision impact the decisions making or the decisions it's tried to execute?
Yeah, I think there's a couple of different ways. So the way that the information is given back. So a lot of what we've seen is if we give it a text representation of the structured information, that has a huge impact on the performance. And so things like, a lot of EHR data is sort of auto-filled. And so if we give it a bunch of like negative things, often it will recognize cases where I don't know, let's say, for example, you're looking at the past medical history and, there's a bunch of no's for like neurological diseases and things like that. There are potentials for it to get confused along that and say, okay, I think that one of these is potentially relevant. So that's sort of on the structured to text side. And then specific to that last project, we are still looking at whether or not the order of information that's retrieved has an impact too. Because yeah, like you said, usually you do like a physical examination and then you order labs and things like that. The LLM doesn't seem to care. And so it'll ask for, it'll start with demographics and then it'll ask for like an imaging result and then it'll go back to like, oh, now give me this lab or whatever. And then it could ask for demographics again. And so I think that also points to the fact that the reasoning processes aren't the same, but also probably impacts performance in some way. So we're trying to figure that out. Yep.
Question about, I don't know that you have a firm answer, but I suspect you have an opinion, which is when you finally brought in you brought in perfectly timing prevalence information.
Yeah.
That's why I was thinking the whole time. Wow,
Mm.
we really have like background level knowledge prevalence. But for some diseases, prevalence changes over time.
Yeah.
Right? And I was wondering if, and that matters both in terms of like whatever case you're looking at, but also the training data. Do you have a sense of being able to associate not only the sort of timing with prevalence changing with time, but also in a way of informing the LLM, as you say, because it's a closed model of the prevalences at like the frequency in the model and a specific point of patient.
Yeah, I think that would be one of the ways that we have to figure out how to frame that prompt, right? So like the specific sort of cohort call out that we would ask in that function would have to have some amount of criteria. So like how old they are, other comorbidities that might be relevant. So those are, I think, what allow us to narrow in on the relevant prevalence for that specific patient population.
Really simplify something like that. You can imagine some areas, for instance, like the HPV.
Yeah.
Adoption, geographic time. If you put something like that, that's highly determinative of cervical cancer. Right?
Yeah, right. Yeah, and there's also, different racial impacts. Some of those might already exist in the LLM, so I think part of it is figuring out where the gaps are. But yeah, either way, I think hopefully it would make a big difference. So
for the deprescribing, the narrow like confidence, bands or uncertainty, how do you think we're going to overcome like that aspect? Because it seems to be a problem with a lot of these large language models in that they have this very narrow kind of confidence interval, and then it's splitting on that. It's making the right decisions most of the time, but then when you ask these types of questions, like you get this kind of very narrow area.
Yeah, it's a good question. I think part of it is figuring out how to get the confidence out of the LLM, and so there's a ton of different like elicitation methods, and we tried a few of them here, but largely like the literature shows that it's very like task dependent, and so we might have to come up with other ways of getting those confidences out. To recalibrate the model itself, I think, is the more difficult question. Some of the things that I suggested might help. Other things might have to do with having a separate reasoning engine on the numeric side. So like the LLM is largely good at parsing text, right? And so how it relates that text to numbers doesn't seem to be reasonable. And so maybe it just doesn't make sense to have it do it all within a single AI model, but sort of similar to, from what I've read, how cognition works, different zones that do different sorts of tasks. So. Oh, yeah. Yeah, go for it. Oh, wait. Yeah, okay. Andrew, you have a question?
All right. Yeah, fantastic talk. Good stuff, and fantastic topic, and thought it was super interesting. My question has to do with differentials, and I'm wondering if you saw a little bit of that intermediate reasoning in the LLM, similar to how physicians might construct a differential. They don't obviously just jump to a diagnosis all the time. So I'm wondering what kind of intermediate cognition you kind of saw there, and how that might affect these future designs.
Yeah, I think just looking at it qualitatively, we definitely saw that in that last project. Basically, actually, you see it in general too. Essentially, like the LM will say, "Oh, it might be this, or it might be this," and I think it's this because of this new piece of evidence. I think there is something interesting to look at there on does it sort of overemphasize that piece of evidence that comes in, and how does that probability distribution change? One of the things that I wanted to do was look at sort of the changing differentials over time, but I wasn't quite sure how to represent that in a meaningful way. But like qualitatively, we definitely see like the LLM at each conversation step will refer back to other diagnoses in the differential. To say, okay, now I think this is more important or this is less important or whatever. So Thanks. Yeah, John, go ahead. And then I see something in the chat, so.
Thanks. Very nice talk. I have one question to you actually with the overemphasizing of especially like recent information. That, like last example when you were conversing with it, and then like querying the Bayesian network. I know that especially older LLMs and maybe not as much the case before have a certain recency bias where they can't get old information.
Yeah.
Did you ever try like reinforcing older information by always including it in the prompt, or is it was the kind of back and forth like?
No, that's a good idea. I probably should try that. But just to confirm what you're saying, I mean, we definitely saw like if the reasoning chain was long, it sometimes gave a diagnosis that wasn't part of the list that was provided because it forgot what the diagnoses were. So there are that recency bias still exists. But yeah, providing some sort of like summary of the information might be useful when.
I guess on that same topic, and I know like a lot of this can be solved by the like suggestion you gave to like retrain on something like this Bayesian network. But did you ever try encoding the Bayesian network in some way, just passing it all at once, or is it way too big to do that?
Yeah, no, I thought about it. I tried it a little bit. Yeah, it's just too big. I think also they're all conditional probabilities, so you have like every combination of the like you know, the different connections into a particular node. And so like even passing in a small number of that was too big. The one thing I did try was passing in likelihood ratio. So like I passed in the top most predictive things, but then essentially what the LLM does is just pick one of those top 5 and it doesn't use any amount of its own clinical reasoning. And so I decided to remove that. So yeah. Okay, I see a question on here. Yeah, sorry to respond to Srinivas's point. Yeah, I agree. I think it's a general limitation of doing sort of these evaluations is just that, yeah, physicians do disagree. There's a lot of variability. Figuring out what the quote unquote ground truth is always an issue. You kind of just have to do your best. So in that deprescribing work, we had a physician evaluate it. We had 2 senior physicians compare to one another and make sure that they agreed. But yeah, in general, like you do have those limitations. It also impacts like the region that you're in, if it's a larger academic medical center versus not, all of these things would have an impact, which is part of the issue that we run into when we have LLMs that are trained on general text predicting in a particular clinical scenario. So cool. Yeah, any other questions?
Just the availability of real world data. I sort of haven't really seen a lot of recommendations like in the community, like on using. Do you think that it's just a limitation of people not having access to real world data to be able to supplement? I agree. I think that that's going to be the way.
Yeah.
In this, or do you think there are some other
I
limitations?
think it's both, but I think the former is probably one of the big ones. All of everything we did here was using Microsoft, and so it's under their sort of privacy layers and things like that. So we still had to pass it through an IRB and de-identify everything. And so that was one of the limitations, is you would have to do that process before passing in that real world data. I think also, yeah, you do have issues of how much real world data you have too, right? So like that's something that only larger academic centers could do. We've talked about before Cosmos, which has a nationally representative sample or something like all of us, would be something we could do. But I think there's a disconnect between the GPT, computational resources and the clinical real world data. Yep. Yeah. Yeah, I mean, one of the limitations was just time and resources locally. So like we would have to run these models locally to be able to access the clinical data. But yeah, the other one is that, up until fairly recently, a lot of the benchmarks show that those are the best performing models. And they're also being implemented in healthcare systems like Epic and locally. And so we thought that integration is something we should evaluate. Any other questions? Oh, yeah, sorry, go ahead.
I actually have a couple of questions about last one.
Yeah.
Slide number 47.
Yeah.
So you're trying to show the confidence of this.
Sorry. We do have numbers, but I don't know where they went. So yeah, this one.
Oh,
Oh, the one before it. Yeah. Okay.
Oh, sorry.
Yeah.
So you try to show how confident.
Yeah.
Is when you actually giving more information.
Yeah.
So did you actually also measure like how accurate it is when you're giving those information? Then associate the confidence with the accuracy.
So we can only test the accuracy. Yeah. Right. So one of the things that we could have looked at was outputting a
After
diagnosis at each
conversations, they
step.
give the
Yeah.
diagnosis at this time.
Right,
then
right.
You can measure how.
Yeah, that's something that I wanted to do but didn't quite get to. But yeah, that is something that I had planned on working on. But right now we just looked at the end. But I agree. I think like being able to see the changing essentially confusion matrix over time would be interesting.
Next slide.
Yep.
Next, the one you said the.
Oh, the overlap one? Yeah.
Yeah. What's this measurement? I actually not quite get it.
Yeah, so what we were looking at was, so we had the Bayesian network output a list of lab tests that need to be run or imaging or whatever. And then we compared what the GPT model selected at each step. And so we just compared those two lists. And so the metric that we used was based on is biased to the rank. And so we looked at is it asking for a certain piece of information at the beginning that's more similar than towards the end? But essentially, it's just comparing two lists of.
So you have a basically two sequence.
Yeah, exactly.
You're trying to compare the overlap. Yeah. And what's the algorithm? Rank-based overlap?
Yeah.
What does this mean if it's 0.1?
It's out of 1, so it's just really, really low. I'm still trying to figure out why this is the case. But like looking at it qualitatively, it seems to be that it's asking for similar pieces of information. But in general, it's not necessarily in the same order. So
yeah, so this is actually back to my first question, right? How this conversation to the LM is asking the right question. Right?
Yeah.
Additional information.
Yeah. I think that is
I think maybe the first step is just compare those two lists, how many are overlap.
right. Right.
Here is 10, here's 12, how many overlap. Right?
Yeah. Yeah.
The sequence.
Right. I don't have that figure, but I did do that. And there was also still not a lot of overlap. So it's not just associated with the order. There's just not overlap in general. Yeah, but I'm not sure why that is. I agree. I think looking at the actual things that it's saying would help infer why that would be the case. I think part of it is we didn't prime it at all to evaluate like a physician would. So we didn't say first do a physical examination, then order vitals or whatever. And so I think that would have more effect, at least in the ordering. But in terms of the general overlap, yeah, I'm not sure why that was the case. Anything else? All right.
Well then, great.
Cool.
Well,
Thank you. Yeah, I'll just I want to thank some people, which I will do. But then you all can leave. And then I'll talk more. But okay, so yeah, first off, thank you to our committee. So Andrew, I've been in his lab for like 5 years now, and yeah, it's been a great time. I've learned a ton. Yeah. And so yeah, I think a lot of the feedback that you've given me over time and just getting me understanding how clinical practice works, and I often have a lot of issues like picking a project and sticking with it, and I think motivation on that end was helpful as well. And yeah, David, I have read far too many papers from the 60s, but I do appreciate it. It is yeah, I've learned a ton of the context and sort of history of our field. And Dr. Hua and Cindy as well. Thank you so much for your feedback, and hopefully more feedback that I will get in written form soon. And yeah, and also, Cindy, you were like the first person I met when I came here. And so yeah, it's been a long time, but I've had a great time. So yes, thank you to all of you. Okay, and so I just wanted to thank our lab as well and all the people that have worked on with these projects. There's a ton of collaborators. We haven't figured out a lab name yet, so I put both of them up there. But yeah, so thank you to all of you, especially the clinicians and physicians that I've worked with. All the annotations I've done, I would not have been able to do without you all. And so that has been instrumental. And yeah, also have learned a ton. So thank you. I won't hold you guys for much longer, but I just want to thank my family as well. And so, yeah, obviously, like all the way from like, having me sit at the kitchen table when I was a kid, learning math, and up until this morning where I realized that I hadn't hemmed my pants. And so somebody had to hem them real quick so they weren't too long. You all have been instrumental. And thank you so much for all of your support over the last few years. And also because it's my PhD defense, I have spent the last 2-3 years taking pictures of Vesh, eating embarrassingly different foods. And so these are all of those pictures, but thank you for all of your support as well. Yeah, and you've helped me a lot, all the way through like some of the math that I struggle with. And so thank you for everything that you've done. But yeah, here are a bunch of pictures of Vesh eating. And lastly, all of the many friends that I've made, thank you all for coming here or joining on Zoom, however you're able to make it. Yeah, I've had a ton of fun and learned a lot over the last 6 years, tons of trips, and hopefully, I would assume are going to stay in touch, but hopefully we get to take many more trips in the future as well. So thanks so much. That's all I've got. Thank you. Cool. Okay. Y'all can go out. There is pizza and cake there. Yeah, feel free to dig in, and I will hopefully see you all shortly. And thank you. Yeah, sorry. Thank you for everyone that joined on Zoom. I appreciate it. Yeah, feel free to reach out if you have any questions. I didn't put my email up here, but yeah, it's my first name, last name at yale.edu. Thank you for joining. Have a good rest of your day. Thank you to everyone. Yep, have a good rest of your day. Thank you for joining.